Okay, so now we're going to start talking about how solutions are classified, and that's going to deal with acids and bases. So you should be able to explain the similarities and differences between acids and bases and be able to apply how concentration affects the strength of those solutions. Okay, so an acid is a substance that releases positively charged hydrogen ions in water. So when an acid mixes with water, that solution will release hydrogen ions. Hydrogen then combines with water to form H3O, which is called hydronium ions. So if you take a look at this example, hydrochloric acid, which is HCl, if you add that to water, the hydrogen separates from the chlorine. So you have hydrogen atoms, or hydrogen ions, chlorine ions, to form H3O, hydronium ions, plus chlorine ions. Acids have a sour taste, they conduct electricity, and they're corrosive. So examples of acids: vinegar, salad dressing, lemons, sulfuric acids, fertilizer, steel, paints, those are all acids. HCl, hydrochloric acid, and carbonic acids. Then we start looking into strong acids. This is how easy hydrogen ions are released to form hydronium ions, even if the concentration is the same. So I'm going to show you examples.
In a strong acid, hydrochloric acid, and a weak acid, hydrofluoric acid. Click on one of the buttons to see hydrochloric acid, HCl, or hydrofluoric acid, HF, dissolved in water.
We're going to click on hydrochloric acid.
Hydrofluoric acid is a strong acid. Strong acids are strong electrolytes, which for most purposes are assumed to ionize completely in water. In this case, HCl ionizes completely to hydrogen ions, H+, and chloride ions better represent white hydrochloric acid donating an H+ to water, producing hydronium ion, H3O+, and chloride ion. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+.
So basically what that is showing you is when hydrochloric acid is added to water, it will completely separate so that all the hydrochloric compounds will separate into H+ or hydronium ions, the H3O, and chlorine ions. That's a strong acid. If you add the same amount of hydrofluoric acid, you'll see what happens.
Hydrofluoric acid is a weak acid. Weak acids are weak electrolytes, which only ionize to a limited extent in water. At equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ions, F-. This reaction is better represented as hydrofluoric acid donating a proton to water, producing hydronium H3O+, and a fluoride ion. Remember that weak acids only partially ionize in water. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+.
So if you look at this example, not all of the HF compounds separate in water into the hydronium and fluorine ions. So that's why it's considered a weak acid. It's not as dangerous because there's still a lot of HFs in the water. So it's not as that H+ or the hydronium ions is what makes a strong acid. So this is very weak acid. Oh, I don't want to do that. Okay. Then if you take a look at bases, these are substances that accept hydrogen ions and form hydroxide ions, OH negative. So for example, sodium hydroxide, that's NaOH, when it gets combined in water, okay, the OH separates from the Na. So you're left with hydroxide ions and sodium. Bases are slippery, they're bitter, they're corrosive, they can cause burns, tissue damage. They also conduct electricity. So soap, shampoo, cleaning products, and your blood is also a base. Now the same rule applies with strong and weak bases. So where acids were how easy hydrogen ions were released, bases are how easy hydroxide ions are released. So lithium hydroxide is a strong base compared to sodium hydroxide. So lithium hydroxide will release more OH ions in water. It makes it a stronger base, more toxic than sodium hydroxide. I don't want to do that. So the way we measure acids and bases is we look at the pH scale. So this is the major measure of how acidic or basic a solution is. So you usually use some sort of indicator to test this. So from 0 to 7, that's acidic. The closer you get to 7, which is neutral, that's a weaker acid. So these release less hydronium ions in water. Or not, hydronium ions. The ones that are closer to 0 release more hydrogen ions, so more hydronium ions, and that makes them stronger and that makes them more dangerous. That's why battery acid is more corrosive than normal rainwater, which is slightly acidic. Okay, same thing over here. Bases are from 7 to 14. If you're close to 7, it's a weak base. They do not release a lot of hydroxide ions in water. So baking soda, you can put that on your hand. You can put it in water and stick your finger in there and it's fine. But if you use lye, which is soap, that's why if you get soap in your eye, strong, and that's a very strong soap, it can damage and burn your eye. Ammonium, it can cause tissue damage because they release more hydroxide ions in water. So to test if a solution is acidic or basic and how strong or weak it is, we use indicators. This is matter that reacts with acid-base solutions and produce certain colors. We've used this a lot with phenol red. Remember if in phenol red in 7th grade we did the photosynthesis lab and you guys blew into the water with phenol red. You blew into it as CO2. It turned pink because carbon dioxide is acidic. Okay, so we've used phenol red quite often. Litmus paper, cabbage juice, those are other types of litmus paper is what you see, those little strips that you're going to be using, and you'll get a scale like that. So if we have a strong or even a weak acid or base and we want to neutralize it, it's very easy to do. A neutralization is a reaction of an acid plus a base. When you react an acid and a base, that's going to produce a water and a salt. For example, lithium hydroxide is your base. We add that with hydrochloric acid, and it makes lithium chloride, which is the salt and water. Okay, so acid plus basis is neutralizing. We use a lot of this in this type of chemistry in upset stomachs. So when you have an upset stomach, you have hydrochloric acid in your stomach. If it's upset, you take an anti-acid or a base like Tums or Pepto-Bismol that's going to neutralize the acid in your stomach. So here's another example. Hydrochloric acid plus sodium hydroxide makes the salt, sodium chloride, and water. Okay, so hopefully you should be able to tell the difference between acids and bases, and you should be able to tell me how concentration and the different strengths and weaknesses of acids and bases, what that's dependent on, the hydronium ions and hydroxide ions, how easily they're released in water.